All right, so now we know all about how to compare data pieces when we're using the median and a 5-number summary and box and whisker plot to summarize our numerical data, right? And again, we're going to use that stuff when we have some outliers or our distribution is skewed because it's going to pull our mean a little bit too much, right? The mean's affected a little bit too much by those things. Now we want to talk about how to compare things, how to compare a data point within a data set, within a distribution, if the distribution is symmetrical, right? Because then we're going to want to use the mean, and the mean, which usually also utilizes, the standard deviation utilizes the mean, so mean and standard deviation go together. So mean and standard deviation on symmetrical distributions is a little bit more meaningful, mostly because the mean means more to people, right? If you talk about an average, that means more to most people than a median does. And so that's where we talk about z-scores, right? Z-scores are a way to give us a sense of how far a data piece is away from the mean in terms of standard deviations, right? It's a nice way to compare. It's also a nice way to compare between two different data sets, right? Get into an example in a second. But to create a z-score, it utilizes kind of the same things as standard deviation and that kind of thing, but we're going to find out how far away a particular data piece is from the mean, right? Subtract it from the mean, and then divide it by the standard deviation. By doing that, we're creating something called, what's called a z-score, but z-scores are measured in standard deviations, right? How many standard deviations away from the mean are you, right? And so we looked at a little bit about the empirical rule, right? And so a z-score will, again, let you know, it kind of takes our data set and transforms it from the original measurement into standard deviations, right? So something might sit one standard deviation away from the mean, right? If you're on the mean, then you're not going to be any standard deviations away. Our empirical rule tells us that 68% of our data, if this is a normal distribution, a symmetric distribution, 68% of our data sits within one standard deviation of the mean. If you remember, 95% of our data pieces sit in between two standard deviations, and 99.7% lie in between three standard deviations, right? So within two standard deviations is pretty usual, right? Those are your usual scores, right? Anything on the outside of two standard deviations really starts to become unusual, right? You're talking about 95% of the data pieces lie in between here. Only 5% lie outside here. 5% is not very high, right? So finding a data piece that sits out there is kind of unusual. Then talk about getting outside of three standard deviations, where 99.7 sit between. And here, kind of hard to show, only 0.3% of our data pieces lie out there. So that's really unusual. Okay? So anything two standard deviations away or higher is really considered unusual. Anything three standard deviations or more away from the mean is considered very unusual, right? So to help us compare between two data sets, right? Is my daughter taller for her age than my son, right? Obviously, I don't have a daughter and a son. I've got two daughters. So this is just an example pulled. Right, so let's say Jessie is 10 years old and is 59 inches tall. The mean height for a 10-year-old girl is 55 inches with a standard deviation of 2. Cody is 12 years old and is 63 inches tall. The mean height is 59 inches with a standard deviation of 3. So we want to see if Jessie is taller for her age than Cody, right? And it doesn't make any sense to compare their heights directly. Okay, Jesse's 59 inches tall. Cody is 63 inches tall. So obviously Cody is taller than Jesse is. But we want to know which one's taller for their age, right? Or for their age and even for their gender. We could do that as well, right? And so z-scores help us do that. We want to create a z-score for both of these two. So for Jesse, her z-score is she is 59 inches tall, and the mean height is 55 inches for girls, 10-year-old girls. The standard deviation is 2. So you subtract these, and you get 2. So this means that Jesse is 2 standard deviations above the mean of 55 inches, okay? Her height is 2 standard deviations. So we'd even want to say that, right? So her height is 2 standard deviations above the mean of 55 inches, right? And probably even I would say above the mean height of 10-year-old girls of 55 inches. Okay, she's 2 standard deviations away, right? Now let's do Cody. So Cody is 63 inches tall, where the mean height of his age group, 12-year-old boys, is 59 inches with a standard deviation of 3, right? So this is going to be 4 over 3, which is going to give you 1.33. So that means that Cody's height is what? You can say, I don't know, almost a standard deviation and a half. Almost 1.5 standard deviations above the mean height. Right? So which one's taller for their age? Well, since Cody is only 1.33 standard deviations above his distribution's mean height, and Jesse is 2 standard deviations above her distribution's mean height, then Jesse is taller for her age, right? So that's how we make that decision. Which one's farther away from the mean? Okay. Now, you can be above the mean, or you can be below the mean. And the sign is where that comes into play. So here we plot out the standard deviations. So again, since Jesse is 2 standard deviations above the mean and Cody's only 1.33, she's going to be taller. So let's say that let's say Jesse's friend is, I'm going to back up for a second. Not Jesse, but Jesse's friend she's not 59 inches tall. She's actually 50 inches tall. She's a little shorter, right? Well, where is she in comparison to other 10-year-old girls? So subtract the mean from her height, divide by the standard deviation of 2. You get negative 2.5. So that means that Jesse's friend's height, her height, is 2.5 standard deviations below. So notice that before I was talking about above, there are 2 standard deviations below the mean. You can't read this, and I apologize. We're starting to run out of room here. Right? Below the mean. So 2.5 standard deviations below the mean would put you right here. So here's Jesse and Cody. Here's Jesse's friend. Right? So the sign on your z-score will give you some idea of whether, will not give you some idea, will tell you if someone sits above or below the mean, and you want to interpret it that way. Okay? So that's how we use z-scores to compare when we're using the mean and standard deviation to summarize your data instead of the median and the 5-number summary.